In this question, we are asked to find the partial pressure of B when the partial pressure of A is 2 atmospheres, and we know the delta G of the reaction is 8.35 kilojoules per mole. So one thing I want to notice right off the bat is that it says that the delta G is 8.35. Well, that does not have the little degree sign as a superscript, so that means we are at non-standard conditions. Well, that triggers use of this equation right here. The delta G under non-standard conditions is equal to the Gibbs free energy change under standard conditions plus R times T times the natural log of the reaction quotient. Okay? And here's our reaction. It really should be written as a reversible reaction. We'll pretend it is written that way. Because we're going to need to calculate Q. Well, we remember from chapter 14 that Q is calculated with the exact same equation we would use to represent or calculate the KEQ, the equilibrium constant. So that's going to be products over reactants. In this case, we're using pressures of the gases since they're both gases. So we have the partial pressure of B over the partial pressure of A squared. Okay? Now, before we can really launch into using that equation, we are missing this delta G under standard conditions. Well, we do know another equation that we can use to calculate that. The delta G under standard conditions is equal to the negative of R times T times the natural log of the equilibrium constant. Okay, the case of P, which we are given. We're given that it is 0.00101. So we can plug in the numbers there. So it's a negative. Now I want to put my value for delta G in kilojoules, and so the value that we're going to use for R is going to be 0.008314 kilojoules per mole per Kelvin. And that number you don't need to know. The 8.314 joules per mole Kelvin is on your equation sheet. We're going to multiply that times the temperature, which we're given is 298 Kelvin, and we're going to multiply that times the natural log of the equilibrium constant, which we're given 0.00101. Okay? Now your units will cancel. Some of your units will cancel. We got Kelvin over Kelvin, and so we got the, don't forget the negative in there. But when you do all that math, you get a value of 17.1 kilojoules per mole. So that is our delta G under standard conditions. So now we're going to substitute that into the equation, okay? And we know that the delta G under non-standard conditions is 8.35 kilojoules per mole. So that's equal to the 17.1 kilojoules per mole plus the R, which again is 0.008314 kilojoules per mole Kelvin. Multiply that times the temperature, 298 Kelvin. And then we're going to multiply that times the natural log of Q. And I'm just going to leave it expressed like that for now. Okay? So when you do the math here, you can take the difference between these two numbers. Okay, move the 17.1 to the other side by subtracting 17.1 from each side. And if you do that, you get a negative 8.75 kilojoules per mole. And then you do the math here, and that's equal to 2.48. So that's going to be 2.48 kilojoules per mole times the natural log of Q. Well, then if you just divide both sides by 2.48, you get a value of a negative 3.53 equals the natural log of Q. Okay? So another way of expressing that, we can just kind of rearrange that or express it as an exponent. And then we could say, well, then Q is equal to E, Euler's number, raised to this exponent, negative 3.53. Well, if you plug that into your calculator, that becomes 0.0293. Okay? Well, I also know that Q is equal to this expression right here, the partial pressure of B divided by the partial pressure of A squared. And I'm told that under these conditions, A is at a pressure of 2 atmospheres. So let's substitute that in. So we said that 0.0293, which equals Q, is equal to the partial pressure of B, and that's what I'm going to solve for, divided by the partial pressure of A, which we're told is 2 atmospheres, and I need to square that. And so then, that's equal to 4, right? 2 squared is 4, so essentially you're just multiplying both sides by 4, and then you'll determine that the partial pressure of gas B, substance B, is 0.117 atmospheres. And that's your answer.